Now, there's a couple exceptions I need to tell you about, and one exception is something called expanded valence. And this can occur in nonmetals that are forming covalent compounds in period 3 or later. And so period 3, remember, is like the third row of the periodic table, and the farther down you go on the rows, the larger the sphere is around that atom. And so we're looking here at the central atom, and the central atom, when they get larger, they don't have to, but they can actually accommodate more either bonding or non-bonding pairs of electrons. And when I say more, I mean greater than 8. So it's called an expanded valence. The valence shell of the central atom can have more than 8 electrons. Here's an example. Phosphorus pentachloride. If you do the A, and I'm not going to go through all of the business because you know how to do it now, but if you do the A and the N, in this case, there are 40 available electrons, and needed, the number of electrons you need to satisfy is 48. Okay, and if you try to figure out the number of bonds then in that case, it's going to say that you only need 4 bonds. Well, that's your first clue that this is probably some kind of an exception, and an expanded valence exception at that. Because once you do there are 6 atoms, and to hold 6 pieces together, you're going to have at least 5 bonds. So whenever this S equals N minus A rule falls down and predicts fewer bonds than you know you must have, that's a clue that this is probably going to be an exception to the octet rule. And so you know you have 40 electrons. Go ahead and draw your skeletal structure with the phosphorus in the center, and then you just put on all of the chlorines with a single bond. And that used 10 of your 40 electrons right there that were available. And then you start putting on your your non-bonding electrons on the terminal atoms. And when you do that, you use up the rest of your 40. And that's actually what we call an expanded valence. The phosphorus has 2, 4, 6, 8, 10. The chlorines all just have 8. We've used all of our available. The prediction thing didn't work anyway because it's impossible to only have 4 bonds in a structure that needs 5 at the minimum. And so that is an acceptable exception to the rule. The phosphorus is big enough to handle it. There's plenty of electrons to make it happen, and everything is stable with it, or all the terminal atoms are stable with octets. All right, here's another example. Xenon Tetrafluoride. And so in this case, again, if you try to do your S and your N rules, the available, in this case, you've got xenon and fluorine. That's a total of 36 available electrons. The needed in this case, if everything needs 8, that would be 40 electrons. Again, when you predict the number of bonds using your rule, you come up with 40 minus 36 is 2. Okay, that's insane. You have 5 atoms. There's no way you can have 2 bonds. So that's your indication that this is not going to follow the rules. Plus, xenon is big. So in this case, you go ahead and you need to make sure you've counted up all your available electrons. All right, and if you put that in the middle, the xenon in the middle, and connect all your fluorines so that the terminal. And then you count up, you've used 2, 4, 6, 8, you have 36 to use. Start satisfying the octets of the terminal atoms, and that's going to get you up to, when you count them all up, 2, 4, 6, 8, 10, 12, 8 plus 8 plus 8 is 32, but you had 36. What do you do with those extra 4 electrons? Well, once the terminal atoms have been satisfied according to the rules, if you look back at your rules sheet, it says place the remaining available electrons on the central atom. And so what you end up with here is the xenon has 4 bonding pairs and then 2 non-bonding pairs on it as well. Okay, it leads to some real interesting chemistry, but that is what it is. Okay, so that's an exception to the rule, and that only happens with the larger atoms, and you know it's going to happen when the rule breaks down and predicts fewer bonds than you need to hold the thing together.